Hello, welcome back to our studies involving aircraft position and warning systems. One of the most common way for the transmitter and the receiver, in effect, to communicate with each other is by way of synchronizing or synchro systems. And that's what we're going to talk about in a little detail right now. As you can see, it looks like a donut type of material. It's colored so that it looks like iron, so it can be magnetized. And you can see there's a pointer and some wires wrapped around the coil, wrapped around the donut. It's used to transmit information from one point to another. So basically the wires are hooked up to a similar configuration, and what happens on one side will also happen on the other by way of directing the magnetism in this case. I hesitated earlier. The word synchro is shortened from the word synchronous and refers to any one of a number of similarly operating two-unit electrical systems capable of measuring, transmitting, and indicating a certain parameter on the aircraft. The class is position warning. This is more the position indicating type system. And there is a number of systems. We'll look at, I think it's the three most common. And there's some differentiation between the different types. This is the one type, and we'll start with this one. Most position indicating instruments are designed around a synchro system, such as the flat position indicator. Fluid pressure indicators also commonly use synchro systems. Synchro systems are used as remote position indicators for landing gear, autopilot systems, radar, and many of the other remote indicating applications. So you can see it's not mechanically connected to whatever is here on the left, but it is electrically or connected by wires. It appears to be three wires going off the screen. The most common types of synchro systems are autosyn, cell-syn, and magnesyn. So they all end with syn, S-Y-N, which in effect is short for our synchronous, which synchro starts with syn. These systems are similar in construction and all operated by exploiting the consistent relationship between electricity and magnetism. In effect, just making a simple electromagnet. If you can control that, you can control the magnetism. The fact that electricity can be used to create magnetic fields that have a definite direction, and that magnetic fields can interact with magnets and other electromagnetic fields is the basis for their operation. And you can see I found an illustration of a synchro transmitter. Now, it's pretty generic. It could work with any of the three so far as what we would know. Okay, the DC cell-syn. First of all, we can see it operates off DC. Direct current, more like a battery type current. That would be over here on the left of the diagram. It's widely used, and you can see why. It's DC for one thing, so general aviation is mostly going to run off DC. It consists of a transmitter, an indicator, and the connecting wires. And we can see the transmitter doesn't look the same as the indicator. Transmitter on the left, indicator on the right in colored. The transmitter consists of a circular resistance winding, and basically the resistor isn't just a short resistor with a wire attached. It's a resistor that is circular in motion. And you can see you can tap into it at different points. It looks like the wires tap into this resistor at points A, B, and C. A rotatable contact arm turns on the shaft in the center of the resistance winding. The two ends of the arm are brushes and always touch the windings on opposite sides. So the little red parts are the brushes. So they're actually touching the windings, which basically affect how much resistance is in the circuit. The instrument on this side basically points between north and east, and it basically is calibrated to agree with whatever the transmitter is sending. We did talk a little bit about direct current, DC. The variable resistor provides a variable current to a coil, so here might be an indication a little bit more of what it would look like. I would presume that this input shaft would be the transmitter side, and the resistor almost looks like a filter, but it is, it's constructed like a filter. And basically the wires are attached to the filter style resistor, and they're set off to this donut structure that we saw in the first slide, which they'll call a toroidal. A toroidal coil, kind of our word for this class. It uses the toroidal coil, which is our donut that is wrapped in wire and in effect turned into a detection electromagnet. And you can see it actually can turn the pointer. Yeah, here's a nice illustration in one of the textbooks. Basically, it's drawn very nice, and you can follow the wires a little closer if you wanted to follow them. We already pretty much know where the wires go into the coil. This slide is to show the lock switch circuitry, which are over here on the side, or on the bottom left. Those can be added to the basic DC Selson Synchro system when used to indicate landing gear position up and down lock conditions on the same indicator. All right, that's getting into it pretty deep, but basically they're illustrating here on whether or not the switches will indicate whether the landing gear is down and locked or up and locked. And that will basically run the indicator off here on the toroidal coil. True or false? A DC Selson system is a widely used electrical method of indicating a remote mechanical movement or position. Yeah, we're all ready to explain exactly how it functions down to the details, and basically they just want a general question. Is it a widely used electrical method of indicating remote mechanical movement or position? Yes, it is. True. How about the second part of it? Again, when you get this test in real life, they won't just give you two true and false questions. They'll give you a multiple choice. Both one and two are true, or one is true and two is not, etc. So far, we know one is true. What's two? A synchro type indicating system is an electrical system used for transmitting information from one point to another. I can't really find anything wrong with that sentence. It certainly is an electrical system, and it does transmit information from one point to another, so that is also true. So, in real life, the real answer would have been both 1 and 2 are true. No problem. So it basically, you have to be able to get 2 true and false questions right in order to get the 1 multiple choice question right. There's a little bit of guesswork. Which of the following are some uses for a DC Sulson system? Now, we did discuss many of them. Let's see if some of this comes back. Landing gear was one, wasn't it? Because it will indicate the up and lock or down lock. So one is one of the uses. 2, angle of incidence of an aircraft. I'm not sure about that one. 3, indicates the altitude of an aircraft. No, it would not be able to do that. So anything with 3 in it is going to be eliminated by itself. So I would just check A to make sure that the other conditions hold true. But to go through the other ones, indicate the cowl flaps. Well, definitely the cowl flaps in the oil cooler door. Okay. I haven't seen that indicator, but I believe it. Indicate the fuel quantity. No. No, I guess it does. I guess that is exactly how the electrical resistance transmitters work. Because it is one of the options in A, so fuel quantity, ordinarily I wouldn't call it we did not study DC Sulson in when we cover fuel quantity indicating systems, but it is kind of interesting. We kind of skirted over that. So a Sulson system is used with fuel quantity indicators. 6, indicate the rate of climb. No. And 7, indicate the position of wing flaps, which is one of its primary purposes. So I'm going to go with A because I like all of them. I wasn't quite sure about fuel quantity, but because fuel quantity is in all 3 options, so it's got to be a use for DC Sulson system. So it's clearly A. Keep in mind, usually with the D2L test, the instructors will usually like to add some other incorrect answers. We don't want to rewrite the question so that you don't find its value. We like to kind of keep it close to what you're going to see on the actual FAA exams, but we don't want you to just we want you to think a little bit. So I personally like to add an option D. I've talked to other instructors who wouldn't even mind adding options E and F. So the fact that you've only got 3, if we beat you up with 4 or even 5, by the time you get to the real test, 3 is going to look like a piece of cake. You're already kind of fighting above your weight class. So basically, what's the rule here? All movable parts of an aircraft, including oil cooler doors, cowl flaps, wing flaps, retractable landing gears. So it's mostly the movement and the position of the moving parts of an aircraft. And they are also used to measure fuel quantity. All right, so that was DC, Selson. This one is AC, Synchro Systems. There's actually two of them. I'm not sure exactly how I set this up. Aircraft with AC electrical power system. Since if you have AC available to you, many make use of the Autosyn or the Magnusyn. So they're both AC electrical power synchro systems. Both operate in a similar way to the DC Selson systems, except that AC power is used. Thus, they make use of electric induction rather than resistance. Current flow defined by the rotor brushes. Magnuson systems use a permanent magnet rotor, such as those found in the DC Selson system, which is actually the part that they test you on the most. What are the differences in the rotor? But you'll see that. I think all the questions are about that. The Magnuson system is an electrical self-synchronous device used to transmit the direction of a magnetic field from one coil to another. So we see we got the AC coming in. This is, as you can see, an old. I draw from all sources, including the old AC 65, is it? What the first generation of FAA certified mechanics studied out of. Magnuson position transmitter. Okay, now we pretty much show the transmitter on the left, but this older diagram, it's on the right. There's some direct linkage. So basically, it's a mechanical arm that basically moves the connection. So it's moving the position of the brushes on. It's not a resistor now. It's going to be some sort of induction component. Let's see here, and it goes through a junction box to the indicator. Doesn't. You can see they've really made the illustrations much better as this has evolved. There's what a Jeppesen figure, and it's still not the newest. This looks like it's 2001. All right, so basically, let's see what we can learn from this. The Magnuson type AC remote indicating system uses the paired relationship of two permanent magnets to transfer transmitter position information to the indicator. So both these are permanent magnets. The blue toroidal coil. The coil is wrapped around a circle. And that's why you don't have a resistor. It's basically where are you in the coil. And a big coil is like an inductor, and that's the inductance that they were referring to earlier. The stator of a Magnuson system is a toroidal coil, a coil wound around a ring-shaped iron core. The transmitter and indicator are not necessarily the same physical size and configuration, but they are alike in their electrical characteristics. So one could be much bigger than the other. Usually the transmitter is larger, mostly because it's got more space, probably in the airframe somewhere. And then the indicator is going to be in the actual instrument case. So it's going to be pretty much under the 3-inch standard. but it actually has the same electromagnetic response of the indicator, rotor magnet, and pointer remains the same. So you can see the pointer is actually going to be this little floating magnet in the middle. A magnet in the middle of a magnet. Okay, they're pointing to permanent magnet in the middle. Okay, that's the difference. You see, a permanent magnet is not attached to electricity. The outside magnet, the toroidal coil, is attached to electricity, so its magnetism, changes based on what it is input. So in this case, the magnet is turned. The permanent magnet is turned, which causes this magnet way over here to turn, almost by magic. This is a nice experiment I would like to set up in the classroom, but there's just so much to do. I'll eventually get to it. Going over it like times like this remind me that I got to move that up on my list. What else do we have here? You can see the AC power supply is our standard of 26 volts, so 400 hertz. So it's not the 100 and some AC. The voltage isn't that much different than the DC voltage if you're running a 24 volt system. And the 400 hertz, that's more applies to AC, so that is the standard for aviation. Are we still talking Magnuson? Yes. Okay, the coil, the middle part is a permanent magnet. The stators, so that's the rotor, and then the stators would be in effect, the stationary portion. It's usually what stators mean, and they're the ones that are wrapped, and they've got the tabs coming in in this case it looks like a D and C, and then the leads are A and B. The rotor and the indicator will exactly follow the movement of the rotor and the transmitter. So basically the experiment would be to turn the one on the left and watch it turn the one on the right. And you can see that makes a difference in where the needle is pointing. Yeah, I've got to do this experiment. It wouldn't be that difficult. And of course, just as I said that, my next slide is to show you how simple it could be. This would be great to have a student wire up this. There's going to be a lot more wire on these coils than what appears. As a matter of fact, it may be not only covering the entire surface, but it might have to come up multiple layers before you actually get the effect that you're looking for. But I don't know that for a fact, so certainly by winding it loosely, I would not expect it to work, but if it did, I would work from there. One of the more popular applications of the Magnuson system is the Magnuson remote indicating compass. So the compass can actually be in effect attached to that rotor in the transmitter. It could be mechanical. There could be a shaft that goes down, and it's actually, as the needle on the compass is moving with the magnetic north, then it is also moving the transmitting rotor below it. That way you can actually have the instrument that you're looking at in the instrument panel. It doesn't have to be flat. It doesn't have to lay flat. So the transmitter is laying flat, and so it's going to give you more of an accurate reading. Than if you try to take your compass and look at it vertically. All right, the questions. The rotor in a Magnuson remote indicating system uses. All right, we looked at the magnet, and it's even called a Magnuson. What is used? Is it the permanent magnet, or is it the electromagnet, which was the toroidal coil stator? We're actually looking at what the rotor is. Or is it both an electromagnet and a permanent magnet? No, it's just that permanent magnet. Yeah, right there. The yellow and green. A permanent magnet. All right, the last type we look at is autosyn. It's very similar. Basically, what happens on the left is going to be mimicked on the right. Basically, it uses the interaction between magnetic fields set up by electric current flow to position the indicator pointer. And a lot of times when you see these delta type windings, that it might not exactly look like that when you actually open up a piece of equipment or etc. So I take these illustrations a little bit for the purpose intended, to basically show you that there's going to be an indicator in the middle, and it's in effect going to be affected by what's going on both sides of the windings, or the other two sides. Autosyn alternating current remote indicating system employs two delta wound coils. Delta, it kind of looks like a D, I suppose, if you tipped it off to the side, as opposed to the Y, which is shaped like a Y, and the three all meet in the middle. This one here is not set up in a Y. It's three, think of it as springs attached to each other, and the wire is tapped off at each of the connections between the three. And they're taken over to their mate on the other side. The rotor is energized by AC electricity, and that is going to, in effect, energize what's going on in this circuit. Although it does not appear to be directly tapped into it, at least not in this illustration. All right. How about in the other one? No? No, the AC power is directly into that rotor and into that rotor. I don't see where it's actually placed into the rest of the electrical circuit. All right, maybe I haven't looked at this that closely. Autosyn system, a synchro system used in remote indicating instruments. The rotors in the autosyn system are two-pole electromagnets, which is why I said you're going to open it up and you're not going to necessarily see delta type windings in here. That's not what you're going to see. But I guess that's what the whole difference is. That's why it's thrown me off a little bit because with the magnesin, the the, the magnet or the rotor is electromagnet, so it's got no wires attached to it, and it's actually the stator that has the wires. In this system, it's just the opposite. The stator has no wires attached to it, but the rotor does, and therefore the rotor in an autosyn is an electromagnet, and it's actually the delta windings as a I stop before I say that it's an electromagnet. I think there's some inducing of electricity based on a magnetic field, but let's go on a little further. Um, they're two-pole electromagnets, uh, and the stators are delta connected, three-phase, distributed pole windings in the stator housings. The rotors and the transmitters and indicators are connected in parallel and are excited with 26 400 hertz AC. The rotor and the indicator follows the movement of the rotor and the transmitter. Okay. It doesn't indicate that that the stator is an electromagnet, so I mean it's a permanent magnet, so I'm going to say it is not. The rotor in an autosyn remote indicating system uses, here it's fresh in our mind. You come back at this 6 months ago, and as you can see, it's probably fairly easy to get magnesin and autosyn mixed up. Keep in mind, magnesin is the one with the permanent magnet. So this one is not. This one's autosyn, so it's not a permanent magnet. What is the rotor? The rotor is actually the electromagnet. What's the stator? The stator is neither an electromagnet nor a permanent magnet. And kind of to conclude it, the basic difference between an autosyn and a magnesin indicating system is the big difference here. We could probably point out some of the more specific differences, but the basic difference is the rotor. One's a permanent magnet, magnesin. One's an electromagnet, autosyn. All right, so I did mention a little bit about fuel. Oh, that was fuel quantity indicator. This is going to be pressure gauges. Let's see why I've included this. We do see our connector here, so our transmitter is on the right. So as the pressure decreases, let's say, all of a sudden the diaphragm expands, and it's going to move. It's got a connection to the rotor. You can see they're not. This is the Y, the other winding that I mentioned. We saw the delta winding. This one is the Y winding. It basically works the same. This may not be the best place to introduce you to it, but they don't have to show the rotor in the middle. Well, they can in the delta, it's easy, but in the case of a Y, they don't have a middle. So the rotor's got to be kind of shown off to the side. AC power is coming in to both sides. What else do we need to know from that? I don't know. Often on twin-engine aircraft, synchro mechanisms for each engine can be used to drive separate pointers on the same indicator. All right, here we do have must be two engines, the left and the right, and you can kind of see the oil pressure for both of them on one gauge. We cover a little bit on how they do that. Basically, they're both attached to one shaft, but one is attached to a different part of the bottom, so it rotates independently of the other shaft. Okay, here they do talk about it. The coil, one behind the other, the pointer shaft from the rear indicator motor can be sent through the hollow shaft of the forward indicator motor. So that's a good way of saying it. There's a hollow shaft and a solid shaft, one and the other, and they operate independently with their own systems. And as you can tell by the picture of the instrument, it's in the older aircraft. Here, this might be a little bit more of what you will actually be seeing. Basically, if your aircraft has digital instrumentation, it makes use of pressure-sensitive solid-state sensors that output digital signals for collection and processing by dedicated engines and airframe computers. Others may retain their analog sensors, but may forward this information through an analog to digital converter unit from which the appropriate computer can obtain digital information to process and illuminate the digital display. So in effect, they're saying that they could still use the old transmitters and sensors, but by running them through this ADC unit, the analog to digital converter, you can actually power an indicator with digital information. So, be aware. They didn't, just because the instrument looks brand new doesn't mean the sending unit is brand new or the latest technology. The end. I guess they have the wind blowing on the transmitter, and the receiver is attached to it. Very nice. Anything more on this subject? All right. I know I'm kind of a little long-winded on this one, but we still got a little bit of time in a traditional class session. So let's look at some of these questions. Fill in the blank. 18. The moving element in the pickup for a DC Selson system is the wiper of an DC system. DC Selson. The first two are DC Selson, and it looks like the last two are AC Magnuson. All right, so the moving element in the pickup is the wiper of or an I don't know. Is this the toroidal coil? Variable resistor. Oh, yeah, I'm way off. The Magnuson, the moving element, is well, let's go to the 19. Sorry, that I just had a little a brain gap there for a second. Yes, it's a variable resistor. It's the one that looks like a filter. So it is actually the part that's moving. 19. The moving element in the indicator for a DC Selson system is the permanent magnet. The moving element in the transmitter of the AC Magnuson system is also a permanent magnet? Yes. And then the coil used for the Magnuson system is a is that the toroidal word? Yes. All right, not the best. Okay, here I get a chance to redeem myself. Just because I'm explaining it doesn't necessarily mean that I'm committing it to memory. The coil used in an AC Magnuson system is tapped so that it has how many sections? Well, we looked at that a few times, and I think 3 is going to be the the answer in most cases. Um, but the coil is tapped in the 3 spots, and that was in the delta configuration. So 3. The moving element in the transmitter for an AC autosyn system is and of course, if the class were right here, we would have other people answering these. So this wasn't really set up for me to answer. Um, this is to encourage class participation. But I got a little bit of time. We're at 41 minutes, so technically we could go for 50 minutes, but we're not going to go anywhere near that. I think this is the last slide. All right, the moving element in the transmitter for the autosyn system. Okay, the autosyn, we saw that the rotor was actually an electromagnet. Now the rotator is usually the part that's moving, though. So I'm going to say that it's the rotor, or it's an electromagnet. Okay. The rotor of an AC autosyn system has a single or a 3-phase winding. Now we did see that a little bit at the end. It is 3 phases, either in the delta or the Y. So it's 3 again. Oops. The rotor. I'm sorry. All right. The rotor, we'd have to go back to show it, but that was the rotor is the electromagnet, and it just has a single winding to turn it into an electromagnet. My bad. I was thinking of the stator, which is the 3 answer in 25. All right, I'm not doing that good on this, but maybe if it was multiple choice, I would have done a little better. No, that was single or 3, so I take that back. It wouldn't have helped. Hopefully, it helped you. And finally, I hope, the Magnuson and Autosyn remote indicating system, both are excited with what? How many volt and how many hertz AC? Okay, we did take a peek at that. What was that? 27 volt, 400 hertz? 26 volt, 400 hertz. All right. You can tell I haven't rehearsed this ahead of time, so I appreciate you bearing with me. It looks like we finally hit the end. So I appreciate you guys hanging with me, and I'll see you on the next one. One more to go before we wrap up position in the morning. All right, we'll see you then.